All right, we're going to work through our next section, 2.7, about absolute value functions. A couple quick things just to know about absolute values that we have touched on at some point, and you should have done some work with this in Algebra 1. But one of the main things is that when we're taking the absolute value of a number, and you're seeing this over here in this table, it's like when we take the absolute value of -3. To take the absolute value means to make that number positive, and that's because, by definition, the absolute value is a number's distance from 0. So the absolute value of -3, we would say that it's 3 units from 0. So that's why it turns to positive. Now, when we take the absolute value of actual 3, so positive 3, it is also still 3 for the same reason, because it's 3 units from 0. So the absolute value of any number means to make it positive. Now, here this is showing our graph. So the graph of an absolute value function is actually two linear equations put together. And this is essentially how we solved absolute value equations, right? When I had absolute value, let's try that again, of x equal to x, so this was a problem that could have shown up on our last test, we'd set the absolute value part equal to positive x and the absolute value of x equal to negative x. Now that's what this is showing, is that when we want to go and graph an absolute value function, it just ends up being two linear functions. Now, this notation of writing it this way, that's called a piecewise function. That's not anything we need to know yet. Mainly what we need to remember is absolute value of a number is positive, and that our shape is going to be a V shape. And there is a vertex. We're going to pay attention to that vertex is going to show up in our equations, and then an axis of symmetry, where that axis of symmetry is always going to pass through the horizontal coordinate of the vertex. Know that the equation of it is x equals, it's going to end up being h. We'll talk about what h is in a second, but x equals some number. That number comes from the x coordinate of the vertex. And let's jump into it. And we're going to, another great thing about this lesson is we're going to talk about some of the transformations we had done previously. So yes, we're working with absolute values, but I also want us thinking about transformations. So it says, what is the graph of the absolute value function, y equals absolute value of x minus 4, and how is this graph different from the parent function of f of x equals absolute value of x? Well, let's start with that. Okay, so y equals the absolute value of x minus 4. How is it different from the parent function? Well, what we have here is this value that is being added or subtracted on after the function operation, right? The function operation being the absolute value of x. When these transformations show up after the absolute or after a function operation, they're going to affect or be our vertical shift. So this is shifting the graph down 4. Okay, and that's all that we need to say. So one way that we could graph this is we could go ahead and graph the absolute value of x, which we have up here. In fact, let's do that this one time because there's lots of ways that we can apply these transformations. So I'm just going to plot these same points that I had for the parent function, which I'll go ahead and use two different colors. So I'll do the parent function in green, so absolute value of x, and 1, 1, 2, 2, 3, 3, and then -1, -2, -3. Okay, so this is f of x, that parent function. And then one way that I can apply this transformation of shifting down 4 is I can take each of these points and literally just shift them down 4. So down 1, 2, 3, 4. That's the new vertex. Down 1, 2, 3, 4. Down 1, 2, 3, 4. Okay, and then we can just add in those points, follow the patterns. Oops, that's a wrong point there. And so now this graph in red, that's our y equals absolute value of x minus 4. So one way to apply transformations when you're graphing them is literally just to write down what the transformation is and apply that to each point. Shift it down, move it left or right. The vertical stretches or compressions get a little bit tricky, but we'll talk about those here in a second. Right, so in general, the transformations of the form y equals absolute value of x plus k affect the axis of symmetry. Explain. Well, if we look at our axis of symmetry for our original function, okay, again, that's going to be the line that draws through the vertex. And look what happens. I'm drawing that line that also passes through the vertex of our new function. So in this case, does the transformation of shifting it up or down affect the axis of symmetry? The answer is no. And the reason is because the axis of symmetry, I'm going to abbreviate that AOX, is the value of the x-coordinate of vertex. And because k affects our y's, right? Our y's are changing. The x's haven't changed at all when we're doing a vertical shift. Our axis of symmetry does not change. Okay, so the axis of symmetry is affected by only horizontal shifts. And let's make a note of that. AOX is affected by horizontal shift. Okay, not vertical shifts. All right. Well, let's keep on going. Graph the following absolute value function. Describe what the graph is different from the graph of the parent function. Again, I'm going to do the same thing. Okay, I've got my parent function, absolute value of x. I see two numbers in here. Remember that everything that is different from our new function compared to the parent function is a transformation. First, we have that plus 3. That's that same k value. That's shifting our graph up 3. Then, when we have a number being added or subtracted inside the function operation being absolute values here, that affects our x's. Okay, that's going to be our horizontal shift. In the horizontal shift, we have to pay attention. That is the opposite side from what we see. So this is actually shifting our graph left 2. And so what I'm going to do is, just like before, I'm going to plot my parent function f of x in green. Don't worry about the axis of symmetry. We don't need to necessarily plot that. Okay, that's our f of x. And so now what I'm going to do is I'm going to take each point, I'm going to shift it left 2 and up 3 to go ahead and come up with my graph of g of x I'm going to do here in green. So let's take this point, let's go left 1, 2, and then up 1, 2, 3. And then left 1, 2, up 1, 2, 3. Left 1, 2, up 1, 2, 3. And then from there, since these are lines, we can actually just use the same slope as if we were graphing a linear function. So in red here, this is our g of x. And we got each point by literally doing these two things to each point. Now, we could have also made a table of values. When in doubt, let's do this right now. Let's say you look at this and you're like, you know what? I just don't remember the transformations, or I've always struggled with identifying them. Well, if you struggle with identifying them, take some values, plug them into your equation. Now, when you're picking values here, you really want to start with, or in the center of your table, so we're going to come up with 5 points, 1, 2, 3, 4, 5. In the center of the table, I'm going to put what makes the absolute value part equal 0. Or in other words, I'm going to match that horizontal shift, which is left 2. So I'm going to put in the middle of my table -2. And the reason that I'm doing that is when I go to graph this point, if I just use, let's say, 0 all the way to 6, well, from 0 to 6, our graph is just going to be a line, right? We're not going to actually see that vertex there. So the reason when I'm saying when you plot points and you want to use this first point that makes a 0, that's how we're going to get that vertex to show up and then get points on either side to create that V shape. So if I don't remember transformations, I'm going to make a table starting with -2 in the middle, and I've got 2 points to the left and then 2 points to the right. And all I'm going to do is plug these values in. So let's see what happens when I plug in -4. G of -4 equals -4 plus 2 plus 3. Absolute value of -4, well, I got to add those first. -4 plus 2 is -2. Then the absolute value of -2 is +2, and 2 plus 3 is 5. So I get 5. Then I do the same thing with -3. Maybe I'll see a pattern here to where I don't need to plug in every single one. So by plugging in -3, got to do inside the brackets first. Absolute value of -1 is 1. 1 plus 3 is 4. Okay, so far it looks like it's decreasing by 1. You know what, let's just do -2, that's going to be 3. And then as soon as I get to the right, I'm going to check this, it should start to see the same y values because of that symmetry that we get with absolute value graphs. So -1 plus 2 is 1. absolute value of 1 is 1, 1 plus 3 is 4. And sure enough, after I get to that 3, I get 4, and one more y value is 5. Those values match exactly what we had already plotted by just applying the points. But again, this is what you would do when in doubt. Okay, if you don't know how to graph a function, pick some x values and plug them in. I know I picked specific ones with the -2 being in the middle, but it really doesn't matter. Just pick any x values, plug them in, and come up with values to plot there. Okay, well, we're going to go ahead and just move right along here. We got a couple more things. Okay, so our stretches or compressions are a little bit different and a little bit trickier to apply the transformations. And with this, I actually don't want us plotting the parent function and these stretch or compressions. First, let's identify the transformation, and then with these, we'll probably just make a table and plot those points. So y equals 1/2 x. This 1/2, that's the a value. That's happening before our function operation. So it's 1/2 times the absolute value of x. So the x's are not affected here. What's going to change is we'll plug in x, and then after we plug in x, that'll get multiplied by 1/2, and thus it'll change the y values compared to the parent function. Now again, I don't really care about that. And first, starting with the transformation here, the 1/2, since that is between 0 and 1, this is going to be a vertical compression. And so if we were to compare it, to the absolute value of x, we should see that it's flatter or wider than that original function. And so now I'm going to plug in some values, x's and y's, 1, 2, 3, 4, 5. In this graph, there's no horizontal shift, there's no vertical shift. And so if I want to follow what I suggested about picking points prior, I want the x coordinate of that vertex or the horizontal shift to be in the middle of my table. Well, since there's no horizontal shift here, it's just going to be 0. And I'm going to plug in -1, -2, 1, and 2. So let's start with -2. I've got y equals 1/2 times the absolute value of -2. Well, the absolute value of -2 is +2, so it's 1/2 times 2, which is 1. Okay, I'm going to do the rest just in my head. So -1, absolute value of -1 is 1. 1 times 1/2 is 1/2. I'm going to write that down as a decimal just because it's a little bit easier for me to figure out where that needs to go. Then I've got 0. Absolute value of 0 is 0. 0 times 1/2, 0. And these values, using that symmetry, are going to be just the exact same from what I got for -2 and -1. All right, so now when I plot these, I've got 0, 0, 1, 1/2, 2, 1, 1/2, and 1. And so this graph, we would say, is vertically compressed by a factor of 1/2. Right, wider or less steep. And we could see that, remember that the vertical compression, it's as if we're pushing down on the sides, or not down, pushing down from the top to bottom. And thus the graph has no choice but to go from a pretty narrow V to just widening out. This is why I can get those fingers to go. All right, well, same thing in B. The difference with B is now we also have, there's actually 2 transformations here, and let's identify those first. First is negative. The negative is a reflection. It's a reflection across the y-axis or x-axis. So this is going to be an upside down V. Then the 2/3. Remember that when deciding if it's a stretch or compression, we really only take the absolute value of that number. And the absolute value of 2/3 or -2/3 is 2/3. So this again is a vertical compression. Okay, so now when I go to plug in points here, we'll just use the same ones. We're going to get some really weird values, but again, that is okay. When I plug in -2, the absolute value of -2 is 2. 2 times 2/3 would be 4/3, but it's negative, so it'd be -4/3, which is equal to -1.33. Okay, the -1, absolute value of -1 is +1. 1 times -2/3 is -2/3, which is -0.66. Absolute value of 0 is 0. 0 times 2/3 is 0. And then we're going to get the same thing on these other values. And so I can just plot those. So -2, -1 and change, -1 and then 2/3, 0, and then same thing over on the other side. Okay, so this one isn't compressed quite as much as what we saw in A there. But it is compressed nonetheless. Okay, compressed and reflected. So both of those things are happening there. Okay, well, now we're going to go ahead and just look at what happens when we apply all these transformations, because there's a little bit more to do. So without graphing, what are the vertex and axis of symmetry of the graph? Y equals 3, absolute value of x minus 2 plus 4. So this brings up a point where we should look at what our function looks like with all the transformations in it. And we did this in our last lesson. So in this case, it'd be a, absolute value of x minus h, plus k. These h's and k's and a's are the same transformations we saw in the previous lesson. H is your horizontal shift, k is your vertical shift, a is our vertical stretch or compression and or reflection. But because h and k, those are our horizontal and vertical shifts, and because the vertex of our parent function starts at 0, 0, our horizontal shift and vertical shift are actually the locations of our vertex. So the vertex in an absolute value function is h comma k. A opposite sign of the h in the equation, and then the same sign of the k in the equation. And then your axis of symmetry, so AOS, is again equal to the horizontal shift. So it's x equals whatever that h value is. All right, so first, looking at our new equation here, let's identify these transformations. This is shifting everything up 4. Then x minus 2, that's inside our function operation. So that's shifting everything the opposite sign from what we see, so right 2. And then this 3 is a vertical stretch. And by a factor of 3. All right, and so after identifying the transformations, let's identify our vertex. Vertex being exactly what we identified as our horizontal and vertical shifts. So it'd be right 2, so 2, and then up 4, so 2, 4. And the axis of symmetry is x equals 2. Okay, so now, and this is exactly what I was talking about if we were to graph this. We don't need to graph it, but a part of your homework, you will be graphing functions in this form. So if I have x, y, and I go to make a table, which is what I'm going to recommend that we do, as opposed to plotting the parent function, shifting everything right 2, up 4, and then applying that vertical stretch, because that can be kind of hard. We're just going to make a table. And so in the middle of my table, I'm going to put the horizontal shift, okay, that value of my x coordinate of my vertex, which is 2. I'm going to take 2 points to the left, so 1, 0, and then 3 and 4. And then you would plug all these x values in to come up with the corresponding y's on your own. Right, the other thing that you could do, and we'll see this kind of as we write equations, is, yes, this is our vertex. 3 is basically like our slope. Okay, these are lines. And so you can treat 3 as your m, and you could go from your vertex up 3 and then over 1 in both directions. Then up 3 again and over 1 again in both those directions. So there's lots of ways that you could graph this particular function. Okay, well, we're going to have to actually do that right now when we go to write the equation of the absolute value function. So we need to identify, so we need 3 things. And that being our values of a, h, and k. The easiest values to find are going to be h and k, as those are just the values of the vertex here. So this vertex is -1, and then 1, 2, 3, 4. So -1, 4. That's h, and that's k. And then the last thing we need is the a value. Now, in this case, the a value is basically the slope. And so I can figure out what is my rise over run for this, and then that'll give me the value of the a, and then the sign depends on whether or not this graph opens up or down. If it opens down, it has been reflected, and thus it is negative. So my slope here, I'm going to put another point right there. My rise over run, I'm having to go right 1, 2, 3, 1, 2, 3, and then down 1. So the rise over run is 1/3. So our A value is 1/3, but since it opens down, it needs to be negative. So it opens down, and thus A equals negative 1/3. And now we just got to plug these values in to the general form of our equation. Y equals, I'll put it right underneath the graph here. Y equals negative 1/3, an absolute value of x plus 1, opposite sign from what we see, and then plus 4. And that's it. All right, I'm going to encourage you to go ahead and pause this video real quick to go ahead and write the equation of this last graph. Once you unpause it, we'll go over it real quick. Okay, so your equation here, the vertex is at 2, negative 1. So in the equation, that's x minus 2, and then minus 1 at the very end, and then the 1/4, that's my new rise over run. Again, it is positive because of this opening up and creating that V-shape. Okay, thanks for watching. You now have a paper assignment to complete. Do your best. There's an answer key posted on Schoology. Have a great rest of your day.